Hello, everybody. My name is Nicolas. For the people who don't know me, I'm a certified flight instructor, a commercial pilot, and today I'm going to present a lesson plan about the airplane weight and balance. Before every flight, pilots must determine the weight and balance to ensure the aircraft operates within the manufacturer specifications. Weight and balance is a safety concern that has cost the lives of several pilots and their passengers when it's not applied correctly. Remember our golden rule as pilots: safety is first. This is an overview of the lesson plan. We have the reference taken from the FAA and official documents, our objective, the key elements, schedule, the equipment we're going to use, instructor action, student actions, and the completion of the standards. Why do you think it is important to learn about the weight and balance of the airplane? Please put all these questions or all these thoughts below. This is a short video of a real life accident. In this accident, a cargo Boeing 747, whose load was not correctly attached, during the takeoff shifted all the way to the back of the plane. Due to this, the center of gravity shifted backwards and the pilots weren't able to have any control anymore of the aircraft. Weight and balance is important in any type of airplane. It works in the same way for any size airplane, just in different scale. Here's some important terms we're gonna know. So, what's the useful fuel? Fuel available for flight planning. Unusable fuel is the fuel in the tanks that cannot be safely used in the flight. It remains inside the system. Basic empty weight, weight on the standard airplane, optional equipment, in-flight fluids, and unusual fuel. What's the payload? Weight of the occupants, cargo, and the baggage. Useful load, difference between takeoff weight and basic empty weight. Maximum ramp weight, max weight approved for ground maneuvers, start and taxi. Maximum takeoff weight, max weight approved for the takeoff run. Maximum landing weight, maximum weight approved for the landing touchdown. And the zero fuel weight, maximum weight without usable fuel. Zero fuel weight for many types of airplane, their worthiness limitations include a maximum zero fuel weight. This limitation is specified to ensure bending moments on the wing routes are not excessive during flight. It is very important to understand all these terms for what I'm going to explain in the rest of this presentation. Now I'm gonna show you how to determine the weight and balance. First of all, we're gonna get these four values. First, the basic empty weight, we're gonna get it from the aircraft maintenance logbook. Second, we're gonna have the people. So there's gonna be passengers. Make sure you ask everybody how much they weigh, how much is the usable fuel for the airplane that we're gonna use, that we're gonna have on board, and the baggage. This is the weight and balance you're gonna get from the airplane maintenance logbook, and the numbers at the end are the ones we're gonna use as basic empty weight. Make sure this is the most updated one. Fuel, very important. In the case for the Cessna 172 or the general aviation small airplanes, we use 100 low lead aviation gas, which weighs 6 pounds per gallon. It has a blue color, and it's important to identify any time because not every plane uses the same fuel. For example, jet airplanes or turbine airplanes, they use Jet A fuel. It doesn't have any color. It's transparent, and the weight of the fuel of this Jet A fuel is 6.7 gallons, 6.7 pounds per gallon. Sorry. So very important to have this information. Here in this case, we have the weight of our pilot and the passenger. We're gonna use 53 gallons times six. That's gonna give me 318 pounds, and we have basic empty weight, total weight. In this scenario, we're not gonna have any cargo or any baggage. Important about this, the maximum takeoff weight. This term in this aircraft, we have um, a maximum takeoff weight, and the maximum landing weight is the same, 2,450 pounds. But then we have a ramp weight is 7 pounds greater. Some airplanes we can put a little more of fuel that can be used for starting the airplane and taxiing, but make sure for takeoff do not exceed the takeoff weight, and then for landing the same. The effect of the weight and balance on flight performance. So we're gonna have some terms here. Center of gravity is the point about which an aircraft will balance. Then we have the datum plane, also known as reference datum, is the imaginary line from which all horizontal distances are measured. These distances are gonna be called arms, and specific points are gonna be called stations. So let's go back here. So the datum plane is a reference point where all the distances are gonna start from. So that's our 0 point. That means in a Cessna 172, like in this case, this imaginary line is located just behind the firewall. That means just behind our flight instruments. From that point, that's going to be our 0 point. From that point, everything is going to be measured backwards in inches, and it's going to give me different stations like the front seats. Then we have the rear seats. We have the baggage compartment number one, baggage compartment number two, and do not forget also where is the fuel located in the wings. So that's another station. So some of the stations can be shifted. In this case, they are just fixed. Then we have the station is a location on the airplane given in terms of distances from the datum. The arm is the horizontal distance in inches from the datum. Then we have the moment. So that's gonna be is the product of the weight multiplied by its arm, also known as torque. And then we have the CG limits, is the extreme forward and aft CG location or center of gravity location. In order to explain how the moment works in relationship with the weight and the arm, I have a door example I like to explain to my students. So we have the hinges where the door is attached, and we have the handle is the outer part of the door. So tell me, what do you think? If you want to close the door, how do you think it's going to be easier for closing it? If you push from the handle, or you try to close it closer from the hinges? The answer is, and I challenge you to do it yourself, it's going to be much easier to close it if you push from the handle rather if you push it from the hinges. Why? It's because there is more arm. The distance from the hinges towards the handle is longer, and that's going to produce more momentum, and that's why we don't need that much strength to close it. Talking about the limits, we have this is a regular envelope of a Cessna 172, which we have weights and we have inches. Everything calculated from the datum plane. So you can see the first number here is 80, 82, 84, All these are distances calculated from the front of the airplane backwards. Everything that can be plotted inside this polygon means it's inside the limits. We can be either too heavy, aft the limit, or forward the limit. We're gonna see the consequences. So what's gonna happen? We have excessive weight effects. Increase the takeoff weight, longer takeoff run. That means we're gonna need more runway, more distance. It's gonna reduce the rate of climb. It's gonna be very dangerous in case you have some obstacles like cranes or trees. It's gonna reduce the angle of climb, lower service ceiling. We cannot go that higher. The airplane is gonna need a lot more power to keep any altitude. Lower cruising speed is gonna reduce the range. That means it's gonna burn a lot of more fuel. It's gonna decrease maneuverability, gonna higher landing speed, longer landing roll, higher stalling speed. Here we have when the CG or the center of gravity is aft. This circle is gonna represent where the center of gravity is located, and this magenta line is gonna represent our envelope. So this is our limits where we should be. Now we're aft. We're gonna have a lower angle of attack, less pitch is required, higher cruise speed, lower stall speed. Till here looks good, right? That means our nose is gonna go slightly downwards, but it's gonna be more difficult to recover from stall. The aircraft can easily develop a flat spin. It's gonna be unstable and require more attention. So, what is gonna be difficult to recover from stall? The rearward part of the airplane feels heavy. Thus, we need to keep the nose down to keep the airplane stable. As the CG moves rearward towards the tail, the arm between the center of gravity and the tail decreases. Thus, the aircraft becomes more and more dynamically unstable. Now, here the example when the CG is forward. It's gonna make our nose heavy. We're gonna need to have a high angle of attack, more downward force required on the elevator. Then we have a slower cruise speed. The stall speed increases. And as I explained before with the door example, it's gonna be more stable. We have long distance from the elevator to the center of gravity. It's gonna be dangerous on landing. Excessive elevator pressure is gonna be required. Weight and balance methods. Here I'm gonna talk about the computation method, the graphical method, and the table method. First, we're gonna talk about the computation method. It's the most used one. So first of all, we're gonna get the basic empty weight as we talked before. From there, we're gonna get the weight, the arm, and the moment for that specific airplane. Then the specific arms for every specific station will be located in the weight and balance section of your airplane flight manual of the plane you're flying. In the case of the Cessna 172, section 6. Now that I have all the arms for every station, I'm going to start with the pilot and passenger. I got the weight, and I'm going to multiply it by the arm, in this case 80.5, and the product is going to be the moment. Then the fuel, we're going to have, for this example, 72 gallons times 6 pounds. We have 442 pounds times the arm. So this is where the fuel is located in this plane. This is station. So 95 inches from the datum plane. These two multiply, we got the momentum. Baggage, 64 pounds. And the arm or the station is located in the 142.8 inches from the datum plane. That means you can notice this is going very backwards of the plane. And the total moment it produces. So now I have my total weight for takeoff and my total moment for takeoff. And that means I can get also my total center of gravity, Remember, it's the total moment divided by the total weight. I get my center of gravity. Now I go here to the right where I have in the y-axis the weight and in the x-axis I have the center of gravity in inches aft of the datum plane, what I explained before. Now I'm going to plot it in my table and I see that I am inside the envelope. That means I am inside the limits. That means we are good to go. Now we know that we're going to burn some fuel up there, right? That means that our center of gravity can be shifted. So how much fuel we're going to burn? We're going to burn 30 gallons. Remember, 180 pounds times 95 is going to give me 17,100. Now I'm going to subtract from the takeoff weight the fuel burn. I'm going to divide this total moment by the total weight. I'm going to have a new center of gravity. And I'm going to go now to the envelope again. And I'm going to check if I'm still inside the limits for landing. So that's my second green point. Is still inside the envelope. That means we're good to go. We have in those envelopes, some of these envelopes, an utility category. If your center of gravity is located in the normal category, you can do maneuvers like the chandelles, lazy 8, steep turns, stalls. But if you want to execute spins, you gotta be inside the utility category. If you execute spins outside of the utility category, you are in danger of producing structural damage to the plane. Now we have the graphical method. This one is very easy as well. We have another example: front seat occupants, rear seat occupants, fuel and baggage area one weight. Uh, at the beginning is going to be the same. Let's go to number one in the sample loading problem. We have the basic empty weight. It's going to be the same. Let's do the example with the pilot and the front passengers. Let's go to number three. We have 340 pounds. So let's go to the left side of the table. We have 340 pounds. We go straight to pilot and front passenger. And when it touches the line, it's going to go all the way down and it's going to give me the moment. So it's 12.7. And that's our moment. The same we're going to do with the usable fuel. So it's going to be 240. Now I'm going to go all the way to the line where the fuel is located. And I'm go now down. It's going to give me 11.5. That's what I'm going to add on my table. The same thing with the rear passengers, 300. It's going to take me to 21.8. Baggage area 1, baggage area 2, we don't have anything. Now at the end, we're going to get the total weight. It's going to be the add of all the weights and the total moment. And remember, the total moment divided by the total weight is going to give me my center of gravity. So we have here the total weight and a total moment. It's my center of gravity and it's inside the envelope, inside the normal category. That means we are inside the limits, but because we are not inside the utility category, we are not allowed to execute spins. But still, we can do like regular maneuvers or performance maneuvers. Then we go to the table method. This one is a very nice way to do it as well. It's just a different method, but it's also very easy one. So here we're gonna take the information from these tables for the same. So we're gonna have our basic empty weight, which is gonna be down here. We have in this table to the left all the information we're gonna gather. We're gonna put it there. So this is already solved, but I'm gonna explain it for you. So we have the basic empty weight. This is the weight we got from, remember, from the airplane maintenance logbook. That's the one we want to get for that specific airplane. Now, to finish filling up the table down there, this complete diagram in the table method is going to give me the information for each of the stations, like the fuel tank, the front seats, the rear seats, the baggage. So it's giving me already what's going to be the arm of each of these values. And depending on the weight I'm going to add in each of the stations, it's going to give me the moment. At the end, I'm just going to add all these values, calculate the total weight, calculate the total moment, and that's going to give me the center of gravity. Okay, let's start with the usable fuel. Main tank's arm is 75. Gallons we're going to use is 44 times 6, 264 pounds, times 75, that is the arm. The product of this equation is going to be the moment for that amount of fuel. Write it down on the table, and let's go with the occupants. Here we have two different stations. We have the front seat and the rear seat, a total of 3 occupants. Front seat is located in the arm and the station 85. It's 85 inches from the datum plane, 130 pounds, and we have another one 170. That's a total of 300, and the total moment 110 and 144. That's going to be 254. Let's see if we have the same numbers. Yes, front seat passengers 300 weight, and the moment 254. When we have for the rear seat, okay, 190, 230. There it is. Now let's go with the baggage. Is this small table right there in the center. So we have the weight is going to be 30 pounds for that amount, for the station 140, a total moment of 42, which is added there. Now we're going to calculate the same as previous examples. We're going to add all the weights. We're going to get a total weight and a total moment. And I did it for you guys. The total moment divided by the total weight have a center of gravity of 81.32, 38, sorry. Here in this table method, there is another way to look at if we are inside the limits or not. So remember the total weight and the total moment. There is a table here on the right side that says weight, and we have minimum moment and the maximum moment. So that's like the envelope we used to use, but in this case it's just a table. So this is the minimum moment we should have and the maximum moment we should have for your specific weight. Our total weight is 2,799. So this table finishes up there, continues, and we find here on the right side the yellow line. It says 2,800. That's our weight. That's the closer one. And the momentum should be between 2,254 and 2,381. Our momentum is 2,278. That means it's between the limits. That means we are good to go. And then finally, up here, we have the moment limits versus weight. There's another way to know if we are inside the limits. So our center of gravity, as we said before, is 8138. You can do your calculations yourself to confirm. Then we have our total weight, and I just here in this table I just interpolate how much will be 2,800 and how much will be the forward limit and the aft limit for that specific weight. So we have the forward CG is gonna limit is gonna 79.8 and the aft 85.2. Our CG is 8138. That means we are between the limits. So we're good to go again. Weight shift, add and subtract. This is very important. So the weight shift, given this example, aircraft total weight, CG station, and the aft CG limit determine how much cargo must be shifted from the aft cargo compartment at the station 150 to the forward cargo compartment at the station 30 to move the CG to exactly the aft limit. So the solution, make sure you memorize these formulas. Then you're looking for the weight to be shifted. So just replace the numbers, the difference of the CG, the total weight, and distance weight is shifted. And the conclusion for this example is exactly 65 pounds weight can be shifted from the aft cargo compartment at the station 150 to the forward cargo compartment at the station 30 to move the CG to the aft limit. This is for adding weight. Remember, if you're adding weight, the CG is gonna move backwards or aft. That means the difference of the CG needs to be added to the previous CG. Then removing the weight, we're gonna do the same thing, but now we're gonna subtract the 1.2 inches that move forward and subtract it from the previous CG. As a conclusion, flight planning is key for pilots to reduce any kind of risks in each of our flights. Proper distribution of weight plays a large and important role in any aircraft overall performance. Load your airplane improperly, and it will affect its fuel consumption, speed, rate of climb, controllability, ceiling, and even structural integrity. Here the practical test standard requirements for this lesson to determine that the applicant exhibits instructional knowledge of the elements of airplane weight and balance by describing weight and balance terms, effect of the weight and balance and performance, methods of weight and balance control, determination of total weight of center of gravity and changes that occur when adding, removing, or shifting weight. If you have any questions, I'll be more than happy to answer all of them. Thank you.